Hi there, welcome to a language presentation of mathematics. My name is Charles Faransipa. Our topic today is Laplace transformations. This presentation is not an introduction to Laplace transformations. I'm addressing this to people who already know a bit of Laplace transform, but I want to explain in such a way that we get to applying Laplace transform to solving difficult questions very quickly. So let's start this way. A Laplace transform is defined by the following improper integral. Now is an integral of f of t multiplied by e to the power st, integrates from 0 to infinity. And after integrating, what you actually get, you get a function of s, where s is a frequency variable, which is given by sigma plus I omega, where omega is equal to 2 pi f. Now, the process of the Laplace transform is actually to transform functions of time. Let's say here we've got the time domain, functions in the time domain. So Laplace transformation transforms functions from the time domain. Let's say here we've got f of t to what we call a frequency domain. Then in this case here, the transformation, the Laplace transform, will take little f of t to capital letter F of s, which is a function, a frequency function representing that time function. I think if we are doing this Laplace transform, you must be aware of the fact that in the time domain, we normally look at functions of time and see how their amplitude change with time. In the frequency domain, the situation is different. We transform this function into a frequency function. Then our horizontal axis now is going to be a frequency axis, and here we're going to look at the amplitude of f of s. So now the plot you're going to get here will show how the amplitude of the function varies with frequency. So that's why we're saying that we'll say that a Laplace transformation migrates time functions from the time domain to the frequency domain. And this is a process which has got actually an inverse process, which we call the inverse Laplace transform, denoted this way, L to the power minus 1. And that's why we can migrate the function from time domain to the frequency domain, and the reverse from the frequency domain to the time domain. Let's look at an example of this nature. What we have here is what we call a unit step function, a function which is 0 from time equal to minus infinity, and when it gets to it's 0, the function is 0, represented by the red graph here, and when it sees 0, it shoots up to 1 and becomes constant forever. This function is a function which is used mostly in engineering mathematics as kind of a signal switch. So if I multiply this function, let's say I take a sine curve from minus infinity running this way, and this as a sine of t. Now if I come up with a new signal here, which is equals to ut multiplied by sine of t, you will see that the curve of this new signal will start exactly at 0 and oscillate towards infinity. Why does it start at 0? Because this unit step before 0 is producing 0, then it multiplies the sine signal, then we don't see it here. It's just a horizontal, coinciding with the horizontal axis there. So now, in this case here, we would like to first of all try to get Laplace transform by the definition using exactly this function. So what we would say now, we say Laplace transform of the unit step function, that will be equals to the integral from 0 to infinity. But you note that from 0 to infinity, the unit step is already 1, so we're going to put 1 there, multiplied by e to the power minus st dt. That was the integral given. Now, to compute this, we have to evaluate this improper integral, by which we're going to evaluate by introducing a limiting process here. In this way, we calculate the limit as t is going to infinity of the integral from 0 to t of e minus st dt. Now, why we introduce this thing? Because this apparently looks like a definite integral, but infinity is not a number. So what we do, we introduce a parameter t here to let it roll towards infinity and see whether this integral has got a limit. And if you've got a limit, then that limit will be the Laplace transform of this unit step. So evaluating this integral, we'll say now limit as t is going to infinity of the integral of this is going to be e to the power minus s t over minus s evaluated from 0 to t. And this simplifies to the limit of, as t is going to infinity, of, in this case here we'll write the common denominator s, and then evaluating there we have minus e to the power minus s capital letter T, minus, evaluating in the lower limit to minus minus, then you get plus e to the power 0. And you note that what we've got here is actually exponential decay. So we would have this decaying to very low value, insignificant values. Then we can say this tends to 0. And then what comes out here, now this is a constant, it does not depend on t, then the answer of this is going to be 1 over s. What we're saying here is that the unit step function has been transformed via Laplace transformation to 1 over s. So, reflecting on the inverse, what the inverse do, the inverse Laplace transform will transform this to back to unit step, that is via the inverse Laplace transform. So normally we would abbreviate this by writing ut, unit step function, and you put here a 2 side of the arrow and say 1 over s, which is the Laplace transform of that. So now I think that is clear. I'll take one more example for another function which is a bit not really constant like the one we've seen. In this case, we're talking about this type of function. We're given here, the signal is xt equals to t ut. So what is involved here, you must see that we are looking at a unit step multiplied by t. In this case, this t represents our usual function y is equal to x, but in this case, the role of x is taken by the time variable t. So, reflecting exactly what we said before, ut before 0, it will be 0. So if you multiply it by that, you will get product 0. In that case, the graph will be transformed this way. It will start exactly at 0, going this way. Then, now to calculate the Laplace transform of that, we need the formula again, which we have as follows. Then we put the t, ut is already 1, so we just put the t and that exponential function e to the power minus st, and that will take us to a capital letter S of t, which would be the frequency domain representation of the time function x of t. So integrating here, this is what we're going to do again. We introduce our limiting process, because it's an improper integral, as t is going to infinity. And then we know that we put a product here. We need to use product rule for integration. Just set our u to be equals to t, and our u prime is going to be equals to 1. And then if v prime is equals to e to the power minus st, then our v is going to be equals to e to the power minus st divided by the derivative argument, which is minus s. So according to product rule, we would multiply these two and have these two under the integral sign. So what we're having here, we're going to have something like this. We're going to have a minus t multiplying these two, minus t e to the power s t over s. Now, applying our formula of integral by parts with the minus sign, and the minus sign, that will give us a positive 1 over s integral of e to the power minus s t. I'll write my limit of integration here this way, from 0 to infinity. What I mean by this, I will finish up integration, then evaluate, and then calculate the limit this way. Then this really takes us to limit as t is going to infinity of this expression, which is minus t e minus st over s. Now when we integrate here, we're going to get exactly this, which is going to introduce the minus sign, and the s will be squared. Then we got minus e minus st over s squared. Then this is evaluated from 0 to t, and the t tends to infinity. Now evaluating this, we have limit as t is going to infinity of, substituting capital letter t, we're going to have minus t e minus s t over s minus e minus s t over s squared. That is the value on the upper limit. Then at the lower limit, when you set 0 here, we're going to have this as 0, but when you set 0 there, we're going to have 1 there, then we're going to have minus 1 over s squared, close, and we close the last bracket there. Now simplifying that, we can see that these are exponential decays, which will all go to 0. So we're left with minus 1 over s squared, which does not depend on t. So our limit ends up as 1 over s squared. So now what we are sitting with here, we're sitting with the fact that u t multiplied by t transforms to 1 over s squared, and 1 over x squared transforms to ut times t in the time domain. So these types of integrals can be carried out with several functions, and can end up producing what we call the table of Laplace transforms, which sometimes we can just use it, apply it without necessarily using the definition to find the Laplace transform. So now the next thing which is very important in this case is the Laplace transform of derivatives. At this point, let's pause a bit. We will resume by starting at Laplace transform of derivatives. Others for now. Thank you for listening.